Hello, Mr. Simpson here with our last recording for Chapter 13. This is 13.4, um, Equilibrium Calculations. At the top here, you'll see our learning objectives. Please take a moment to pause the video and write these in your notes. All right, in this last section, we're going to expand a little bit on our calculations using equilibrium constants. There's basically three types of equilibrium calculations we're going to look at. I'm going to do an example problem of each, but those are calculation of an equilibrium constant, calculation of missing equilibrium concentrations or partial pressures, and then finally calculations of those concentrations or pressures from initial. I think the best way to kind of talk about each of these is to actually look at an example. So here's our first example, and this is going to be calculation of an equilibrium constant. So please pause your video and put this practice problem in your notes. So as always in a chemistry problem, we want to take a look at the problem and try to identify, okay, what's the problem asking for, and what is the problem giving me? So as I can see here at the bottom, at the end of this problem, what is the equilibrium constant is what the problem is asking for. Okay, so I know what that means, that I know how to come up with the expression for the equilibrium constant. That's going to be the concentration of I3 minus over the concentration I2 times the concentration of I minus. So there's our expression. So now if I have the equilibrium concentration of those values, I just plug them in and I can solve for my equilibrium constant. So we know what the problem is asking for. Now, what is the problem giving us? This is where we run into a little bit of an issue. So if you look here, this value of concentration for the I2 and I minus is before the reaction. Okay, so those are not equilibrium concentrations. This is an equilibrium concentration. Change my color again. So this is an equilibrium concentration for the I2. So I have to do some work here to get all three of my equilibrium concentrations. And here is where an ICE table comes in. So I'm going to rewrite my reaction down here, or at least my species. And we're going to construct an ICE table. An ICE table identifies our initial concentrations, our changing concentrations, and our equilibrium concentrations. Okay, so as I look at what data is given to me in the problem, we have an initial concentration for the I2 and the I minus as this amount. And that makes sense that they give me just the initial concentrations of my reactants, right? Because when my reaction starts, all I have is reactants. So my initial concentration of the I3 minus would be 0. Okay, so now as we know, reactants are going to get used up, so we're going to lose some concentration of these two reactants, and products are formed, so we're going to gain some concentration over here. Now, it doesn't come into play here because the stoichiometric relationships here in this balanced equation are 1 to 1 to 1, but in this change line, I would take into account stoichiometric relationships. So let's say if there was a 2 in front of something here, it wouldn't be minus x, it would be minus 2x or plus 2x. Okay, so we'll see some examples where that is the case. All right, finally then we get our equilibrium concentration. Now, if as I look back at the problem, they actually give me the equilibrium concentration of I2. So that's very helpful and makes this problem on the easy side. So I can put in here my calculation, my concentration of I2 minus. And because I have the initial and the equilibrium for one entire species, that means I can then quickly calculate what this change value would be, what these x values will be. All right, so since the difference here between 1.00 times 10 to the negative third and 6.61 times 10 to the negative fourth is something I can calculate quickly just by subtracting, I can do that and I get 3.39 times 10 to the negative fourth. Okay, so again, over here, we're going to be subtracting that amount. and that amount would be exactly the same here for my other reactant. And then on the product side, we would be adding that amount. Okay, so that means that my equilibrium concentration for my I minus is going to be the same actually. That's not always going to be the case, but since they gave us the same initial for both, that's what's going to happen here. And then my equilibrium concentration for my product is going to be that 3.39 times 10 to the negative 4. All right. Now that I have those values, I can come back up here to my expression, and I can plug those values in. So 3.39. Again, there are no coefficients, so there's no exponents to worry about here. If they were, we can do our expression. We've done enough of those at this point. Okay. And when I do that work, I'm going to get an equilibrium constant of 776. Okay, this is the first type of problem that we talked about of the three types, calculation of an equilibrium constant. What makes this one a little easier is the fact that in one for one species, I had both. Oops, that's not what I wanted. I had both the initial and the equilibrium, so I could calculate that change, which then made it easy for me or possible for me to get all three of these values. You're going to see in a minute in our other examples that is not always the case, and therefore the problems get a little more complicated. Okay, calculation of a missing equilibrium concentration. So why don't you go ahead and pause the video for this next type and copy this problem in your notes. All right, so as I read through this problem, and I'm looking for what is this problem asking for, this is asking me to calculate the equilibrium concentration of NO gas. Okay, so I have a reaction. Obviously, that is going to be important. So I'm actually going to just rewrite that reaction down here. And we have, if we are given a equilibrium constant Kc, obviously, if I'm being asked to solve for concentrations, I'm going to need to know that equilibrium constant in order to do it. Okay, so since they've given me an equilibrium constant, I know that I must be dealing with or need this expression. So there's our expression for our equilibrium constant. Okay, so now I can go back to the problem and see, okay, what is the problem giving me? Here I can see that in addition to the Kc value that I already highlighted here, we are also given the equilibrium concentrations of N2 and O2. All right, so as I think about all the information the problem has given me, I have a Kc value. I have an equilibrium concentration of N2. I have an equilibrium concentration of O2. And what I'm missing then is my equilibrium concentration of NO, which is exactly what the problem is asking for. So I'm now at a point where I can work to solve this problem. Now we're ready to solve. So I would first multiply my values together here with the 4.1 times 10 to the negative fourth. And I would get a value of 1.31 times 10 to the negative 7th equals my concentration of NO. And that value is squared. So if I take the square root of both sides, I would get my concentration of NO equals 3.6 times 10 to the negative 4th. Go ahead and check that on your own work there and see if you've come up with the same answer. It's always possible, we can always check ourselves here. We can always set this back up and make sure that when I plug in all my values here, and solve for k, that we do in fact get the equilibrium constant that we were given in the problem. So you can always check your work at the end as well to make sure that things worked out correctly. Okay, now we're going to get into the most complicated scenario of these calculations. So please go ahead and pause the video and copy this problem in your notes. Now, as I look at this problem, you can see the first wrinkle is they do not actually give me a reaction here. Now they describe it, so I can, I'll be able to determine this value, this reaction pretty simply. But, whenever I do something like this, I want to make sure that I end up with a balanced equation. Okay, so I need to, I need to make sure that I end up with a balanced equation. It just so happens that this particular equation is balanced. Okay, they give me the Kc again, so that's going to end up being important. And you can see here that what the problem is asking for is the equilibrium concentrations. What are the equilibrium concentrations of all three things? So a lot of information to find here, and not a lot of information given. The only other piece of information given is that PCl5 has an initial concentration of molar. Okay, so here we are back to an ice table, right? So that's my initial. My initial for my products are going to be 0 and 0. My change, I know on this side I'm going to lose some concentration of PCl5, is going to get used up. And over here, I'm going to gain some concentration. Now, I don't have any other information, so I cannot figure out what this change is going to be. So I'm left with my equilibrium concentrations being 0.100 minus x, minus some amount of PCl5, and then just x and x over here in my products. So when I think about what my expression is going to look like, okay, my Kc is going to be the concentration of PCl3, concentration of Cl2, all over the concentration of PCl5. Okay, so now I have a situation where I have x times x over 1.00 minus x. Okay, and when I set that up with the Kc value that the problem gave me, I'm going to get 0.0211 equals x squared over 1.00 minus x. I'm going to get this expression here. Okay, so now I have some math work to do. So the first thing I'm going to do is if I cross multiply those values there, so I'm going to get 0.0211 times 1.00 minus x equals x squared. And I'm going to get an expression here, x squared plus 0.0211x minus 0.0211 equals 0. Now, in order to solve this, I'm going to have to use the quadratic equation. Okay, so anytime I have an expression like this, we have this idea that I'll just write this in here. This is A, this is B, and this is C. All right, so I can set up and solve for the quadratic. If you remember, to solve for x, quadratic equation looks like looks like this. Now I can plug my values in. Okay, x is going to equal b is negative 0.0211 plus minus the square root of 0.0211 squared minus 4 times a. Oops, actually put the number in, we'll need a. Times C. And this would all be over 2a, which is 2 times 1. All right, as I work through that, I'm going to get 2 answers as I solve this, right? As always in the quadratic, because of this plus minus situation. As I work through and solve here, I'm going to get x equals 0.135 or x equals negative 0.156. So if we think about what x signifies here, as I look back up to my ICE table, I'm going to try to keep it right. So what did we call x up here in our ICE table? We called x the concentration of different values up here, right? So x is a concentration, so the negative value doesn't make any sense here. So that's not going to, our answer is always going to be the positive value. All right, so now I can say that the I can I have my answers now, where I can come here and say we called the concentration of PCl3 X, so that means that value is 0.135. We called the concentration of Cl2 X, so that means that's 0.135. And we called the concentration of PCl5, all right, if you remember, we called that concentration 1 minus X, okay, 1 minus X. So that means the concentration of my PCl5 is going to be 0.87 more. Okay, that's how we have to work the situation if I do not have any other information except the initial concentration, and I'm being asked to solve for the equilibrium concentrations. You can see the difference here between that and when we were solving for equilibrium concentration here is I had more information. I was only missing 1, all right, of a missing equilibrium concentration. Here, I'm being asked to solve for all the equilibrium concentrations. So I have to do my ICE table. I'm going to end up in some situation like this. I'm going to end up with an expression in which the quadratic is going to need to be used. And then I'm going to solve for x, take the positive value, and then just rewrite, make sure that we identify what we call these things. Remember, in a balanced equation, you could have different coefficients here, right? So this could be 2x, and this could be x, and this could be 1 minus 2x. So you're going to see in some different problems, you're going to see the stoichiometric relationships here change, and therefore some of my values that I'm going to solve for will change. We'll solve for x, and then we'll apply that accordingly in order to actually get the equilibrium concentrations. Okay, we're going to have a couple practice problems like this on the quiz, and then we'll get into some more in class time. That's it for this section of Chapter 13 and for Chapter 13 as a whole.